Hi, my name is Escher Barrett, and this is Physics 2212 Lab 2 Charge Tapes Revisited. So the purpose of this lab was to create a computational model of two charge tapes as lines of charge rather than point charge. That basically means that instead of generalizing all the charge on the tape as one singular point, as we did in Lab 1, this time we're going to split the tapes up into different segments of charge and then use that to calculate a more precise charge for the tape, to therefore then estimate the amount of charge on each tape necessary to float one above the other. Our findings, quick synapse, is that the electric force of the bottom tape on the top tape was 1.962 times 10 to the negative 3, and the charge of the tape is described as line charges is 2.649 times 10 to the negative 9 coulombs. Fundamental principles is the same as in Lab 1. We're going to use the electric force formula, Coulomb's law, which is just the force of attraction or repulsion between the two charges. And then we're also going to use Newton's second law. Very basic, just that the net force of the object is the change in momentum divided by the change in time. And then the force of gravity, which is specifically the force of gravity near Earth's surface, which is just mg in the negative y direction. Recap in Lab 1, because we're going to use the same sort of initial conditions and the system of surroundings for our lab now. The system will be the top tape, and the surroundings is going to be the bottom tape and the Earth. What we found in Lab 1 was that the charge of one tape is 1.4 times 10 to the negative 9 coulombs. Now, to begin on the computational model, you can see in the top right, I have the constants written out. The top one is the Coulomb's constant, and we have the gravitational constant, and then the charge that we found in Lab 1, and the mass of the tape. And we see this first snippet of code is basically just creating the electric field at the particle and the location. And then this next snippet of code is creating the line charges, and basically how it's doing that is with the for loop at the bottom. It's basically iterating each charge. Continuing that, we have the top tape and the bottom tape as they are going to be sort of visualized in the coming results. And for the next snippet, we're calculating the electric field and the electric force on the top due to the bottom in both those lines of code in that nested for loop. So basically we're calculating that for each charge on the line. That's what these for loops are for, to continuously calculate that as the program runs. Alright, now on to results. So on the right there you can see the model that was created when we ran the code. The electric force in the arrow pointing up, the gravitational force in the huge arrow pointing down, and then we can see the top tape is in red and the bottom tape is in blue, while the electric field generated by the bottom on the top is in the green arrows. I split it into about 50 segments, so there should be 50 green arrows there. So we found the magnitude of the electric force to be 1.962 e to the negative 3, and the magnitude of the gravitational force being the same, which makes sense because the tape is floating motionlessly. We had to make some assumptions in this lab. These are pretty basic. We ignored air resistance. We said that the charge is uniformly distributed and that both tapes have the same charge. Some possible error, basically from Lab 1, when we were doing the actual experimental portions of it, we were finding that Q value. Lab 1 experience, the measurements could have been off, and handling of the tapes in Lab 1 could have reduced charges. So just some human error from previously. Now, for calculations, so we know the net force to be 0, and we know the gravitational force, so by algebra we can figure out the electric force. And then once we find that, we plug that into the equation for the electric force of a rod, and solve for Q, which we found to be 2.649 e to the negative 9. Now, for discussion, what if we had modeled each of our tapes as a single point charge like in the previous lab? As we see in the previous lab, the point charge was 1.4 times 10 to the negative 9, and the line charge was 2.649 times 10 to the negative 9. So we found that the line charge actually showed a greater value than the point charge. But why do these differ? Which value is more likely to be closer to the real value? So the line charge was calculated with more precision than the point charge, which is why they're a bit different in value. And this precision is why the line charge is closer to the real value, because it was split into smaller segments that is better than generalizing into one point as we did with the point charge. Thank you for listening.